part 4 of lecture 4 is on calorimeters. Let me give you some introduction. Now, calorimeter is a detector concept that aims to measure the energy of a particle by stopping it. A calorimeter, therefore, is a detector which fully absorbs the particle. You have an incoming particle that showers in the detector volume. The shower consists of secondary particle, and ideally the full energy of the incident particle is detected in the detector, and the detector response S is ideally proportional, a linear function of the energy of the incident particle. So the incident particle in calorimeters showers, and the secondary particles then deposit the energy and produce further particles until the full energy is absorbed. The showers that ensue from the collision of the primary particle with the detector volume differ in composition and in shape depending on the type and the energy of the primary particles. Calorimeters are used for electrons and photons. Those are the electromagnetic calorimeters, and for hadrons. These are called hadronic calorimeters. Ideally, but unfortunately not in practice, the response of the calorimeter signal is linear for both the electromagnetic and the hadronic interactions. We'll discuss what a difference in the response of the two energy component means, and let me say now that in practice this principle unfortunately is violated for most materials and detector concepts. Calorimetry really is a widespread technique in particle physics, similar to silicon trackers. Instrumented targets also comprise neutrino experiments, proton decay experiments, where very large volumes of water tanks are used to observe decay products of a hypothetical proton decay. The proton is stable in the standard model, but certain models beyond the standard model predict the decay of the proton. And the measurement of the decay products is calorimetric, and for example, also for cosmic ray physics. In collider experiments, calorimeters cover usually the full angular surface area, 4 pi of the detector. Calorimetry is a detection principle. It makes use of various detection mechanisms, all of which, in fact, we have already discussed. There are scintillating calorimeters. It works with Cherenkov radiation, with ionization, and even with cryogenic phenomena. Imagine a particle hits a detector volume causing a shower, as is shown here to the right. Many signals can be produced simultaneously, and those can all be used in calorimeters. There's an electrical signal, for example, from ionization. Then there is an optical signal, the scintillation light. There is a thermal signal that's difficult to detect. However, in cryogenic detectors, it is possible, and there is also an acoustic signal. All these mechanisms are used in certain calorimeter detectors. We will discuss only a few of the main concepts. But let's view the main calorimetry principles from the perspective of a general purpose particle detector now. Calorimetry measures both charged and neutral particles. The performance of the calorimeter improves with the energy, and it's more or less constant over 4 pi. We need to compare this to a magnetic spectrometer, which is a tracking detector, for example. A magnetic spectrometer has a strong anisotropy because of the B field. The transverse momentum measurement works by bending the path of a charged particle traversing the detector, and the curvature of the trajectory only depends on the transverse momentum, not on the longitudinal momentum, and hence there is an anisotropy. Calorimetry is based on a statistical process. This is the stochastic shower development of the incident particle in the detector material. So let's say we have an electron or a photon hitting the detector volume, and then it produces an average number n of secondary particles. N hopefully is proportional to the energy. So we have a number of n particles per, let's say, GeV of energy of the incident particle. The energy resolution is then in principle at least dominated by statistical fluctuations of n. Sometimes you see a little bit fewer particles, sometimes you see a little bit more. The relative energy resolution, because of this stochastic feature, therefore improves with increasing the energy. That's because the statistical uncertainty of in the limit of large particle multiplicities falls with the square root of n. And hence the calorimeter measurement, the relative uncertainty in the calorimeter measurement drops with 1 over the square root of energy. Compare this to the spectrometer measurement, where we deduce that the resolution in the momentum measurement is proportional to the momentum. We discuss this in a little bit more detail, but here we only take the bird's eye view. Compare this, let's compare these two dependencies. To the right, we see a very schematic comparison of the resolution, that's the relative resolution, sigma over E, of the calorimeter, and spectrometer measurements. These are typical hadronic and electromagnetic calorimeters. They're compared for different absorber materials here, iron and uranium. We'll see a few examples, but what you see is that versus the logarithm of the particle energy, the resolution drops for the calorimeter because of the stochastic nature of the shower, and it increases for the spectrometer measurement because the curvature of a particle at high momentum is more difficult to measure, as we've discussed in the last lecture. And therefore, to cover the full momentum range, this is in GeV, by the way, to cover the full momentum range, both detector principles are needed in a general purpose detector. The required thickness of a calorimeter scales only with the logarithm of the particle energy. It's something that we will derive from general shower properties. Calorimeters can also be used to identify the particle type in case the readout has sufficient granularity to fully resolve the fine structure of the shower. If that is the case, then one can infer from the shower profile what species the incident particle was, because particles, electromagnetic and hadronic particles, leave different shower shapes. Calorimeters are furthermore important components of a trigger system. The trigger system is the electronic system in the detector that selects the events to be recorded. Not every event, not every experiment is a trigger system, But if for example, the collision rate or the incident rate of the initial rate of events is too high to read out the full detector, then the readout frequency must be reduced and only the most interesting events be recorded, and that is done by a triggering system. Most of high energy physics experiments have a trigger system. In the calorimeter, it's possible within a few nanoseconds to gather and analyze in a coarse manner complex information on the particle energy, particle direction, the topology of the event, like how many jets there were, and possibly also to compute whether the event has missing energy, which is the telltale signal, for example, for neutrinos. So with calorimeters, with a limited number of readout channels, on a very short time scale, one can derive and obtain general properties of the events, and based on these properties, then decide in a customized electronic, for example, whether the detector should be read out or whether this event need not be recorded. Good, so calorimetry is important. Let's go through the calorimeter types. There are two different calorimeters just by construction. The first type are homogeneous calorimeters, shown in the sketch at the bottom left. For a homogeneous calorimeter, the particle is stopped fully in the instrumented region in the detector volume. So the detector volume is, the full detector volume is the calorimeter, the sensitive material. The second group are sampling calorimeters, shown to the right. A sampling calorimeter consists of a passive absorber, which is not instrumented, interleaved with detectors, shown in green here. That's one big, that's one way to separate the types of calorimeters. The second way to separate calorimeters is by their use case, their application. The two main applications are an electromagnetic calorimeter. Electromagnetic calorimeter is based on the electromagnetic interaction and thus measures the energy of the electrons, the positrons, and the photons. Remember, a highly energetic photon incident on a detector material will pair produce electrons, and electrons then subsequently at high energies will undergo Bremsstrahlung processes. All these are driven by the electromagnetic interaction, and the characteristic length scale is the electromagnetic interaction length. And when we compare a 100 GeV electron on a block of iron and a 100 GeV pion on a block of iron, we find that the electromagnetic shower is much shorter than the hadronic shower, because in the hadronic shower, neutral particles can travel large distances and thus penetrate deeper in the calorimeter. Hadronic calorimeters measure the energy of the hadrons. It's not possible to have a homogeneous hadron calorimeter. The hadronic shower are you see, this is 1.5 meter of iron and a 100 GeV pion. It's not possible to replace the iron with a scintillating material for example, in a collider experiment. The stopping power would be too low. So hadron calorimeters always are sampling calorimeters. One needs a passive absorber to keep the penetration depth at bay, to have the hadronic shower develop on short length scale. Electromagnetic calorimeter can both be homogeneous and sampling. Both are possible. Let's talk about homogeneous calorimeters. So the defining criterion is that for a homogeneous calorimeter, the detector material is at the same time the absorbing material and the detector. Examples of different signals that are exploited in homogeneous calorimeters are, for example, the scintillating light. That the example that I know best is the lead tungsten calorimetry from the CMS experiment, but other inorganic crystals can be used. Then Cherenkov light, for example, in lead glass, or ionization. Ionization, for example, in liquid noble gases, argon, krypton, xenon, but also the ionization signal from semiconducting detectors. The high luminosity upgrade at the LHC experiments partially feature semiconducting calorimeters. That's a new development in Proton in the past years. We have now understood how to, well, we have now optimized, I think, in the community, how to build silicon tracking detectors. Now we're moving to silicon calorimetry, which allows extreme granularity. But let's move on with the overview before we go to the detail. What's the advantage of what are the advantages of a homogeneous calorimeter? The most important one is that the energy resolution is the best that's achievable with the given material. That's because the full detector volume is instrumented. The disadvantage is that is expensive. As we said, the homogeneous calorimeters are only used as electromagnetic calorimeters, which measure the energy of electrons and photons. Now, sampling calorimeters consist of alternating layers of passive absorbers, shown in blue here, and active detectors. Typical absorbers have a high nuclear number. You want a large atomic nuclei to have a large stopping power for strongly interacting particles like pions, neutrons, protons. Typical absorbers are iron, lead, and uranium. The first two are cheap. Uranium is expensive. Typical active detectors span a very wide range. The cheapest ones are plastic and crystal. Well, the cheapest one is a plastic scintillator. Crystal scintillators can also be used. Silicon detectors can be used, as I've mentioned before. Liquid noble gases can be used. Atlas, for example, uses liquid argon. But also gas detectors can be used. It all depends on the budget, the detector application, the rate, and the energy of the particles that are expected. The advantages of sampling calorimeters are that they are more flexible in the design because there's an absorber and there is a detector. So the materials can be chosen and the sizes of the geometric proportions and the sizes of both the absorber and the detector can be chosen independently. So that allows more handlers to optimize a sampling calorimeter. For example, by choosing a very dense absorber, the calorimeters can be made very compact. These compact calorimeters are then cheap in comparison to homogeneous calorimeters of the same size and with the same detection principle. The disadvantage is obviously the shower part that's lost in the absorber is not measured. Hence, only a fraction of the incident energy is deposited in the detector layers. And if the absorber is thick, then the energy resolution therefore reduces when compared to a homogeneous calorimeter. We then speak of sampling fluctuations because one particle may deposit a certain number of particles, a certain number of secondary particles in the detection material, but the next particle may lead to a different shower, providing a yielding a different number of particles in the detection material. You don't know how the shower development looked like in the absorber, and hence you incur an uncertainty on the energy measurement that degrades the energy resolution. Sampling calorimeters come in a large number of different configurations. Let's look at the top left. That example is a calorimeter with a scintillator. It's reminiscent of the CMS Hadronic Calorimeter, which is a plastic sampling calorimeter. So here we have a plastic scintillator with an absorber. The scintillator is connected via a light guide to a photomultiplier. The direction of the incoming particle is where my mouse cursor is going now. So it goes in this way and showers mostly in the absorber and is reconstructed. Well, not reconstructed, record, and the signal is, the scintillation signal is recorded by the detector configuration. Then to the right, an example with multi-wire proportional chamber that reads out the ionization charge. The principle is the same. Particle comes from the left, traverses these segmented layers of absorber and detectors. And here, a multi-wire proportional chamber reads out the ionization charge. Reading out the ionization charge improves the resolution in the energy measurement. Sometimes it is enough to know that a signal was recorded. So sometimes the count rate is enough, in particular if there is a large number of wires in the proportional chamber. Bottom left, the liquid argon Atlas calorimeter is operated at cryogenic temperatures. There's also an absorber that is completely immersed in liquid argon. The advantage of liquid argon here used for an electromagnetic calorimeter. So we have an electromagnetic, it's an example of an electromagnetic sampling calorimeter. The advantage of using a liquid noble gas is that it can be purified over the lifetime of the detector, and hence the radiation damage is limited to the electronics and other parts of the detector. But the sensitive material, in this case liquid argon, does not degrade through radiation damage because it can be exchanged. That's a very big advantage of liquid argon and liquid noble gas calorimetry. A funny example, I think, is the Shashlik calorimeter shown to the right. That is there was the Hera B calorimeter at DZ. It has scintillating, wavelength shifting fibers immersed in the direction of the incoming particle in a scintillator and interleaved with an absorber. So the absorber accounts for the showering of the incident particle. Then the shower develops, scintillating light is produced in, I believe that was plastic scintillators, and the wavelength shifting fibers take out the scintillating light and connect it to the photomultiplier tube. So that's the Shashlik configuration. Good. Let's discuss a few details on electromagnetic calorimetry. To understand what electromagnetic calorimeters do, we need to look at the shower development. We have done so in lecture 3. We'll do so again now. Some of it will be repetition, but that doesn't matter, I think. So electromagnetic calorimeters should measure the energy of electrons, positrons, and photons. Remember from lecture 3 that the important processes of energy loss of electrons are the Bremsstrahlung, at least at high energy, that's completely dominant. The energy loss is therefore proportional to the energy itself, and the characteristic length scale at which this happens is the radiation length x0. For photons, the process is pair creation. So a photon in the vicinity of a nucleus can create an E+ E- pair. And because if you compare the top and the bottom diagram, actually all the number of ingoing and outgoing particles is the same, which means if you do a quantum mechanical or quantum field theoretical calculation of the process, the probability of these two processes to happen are related, and hence the mean free path of a photon in the same material as an electron are related, and the factor is 9/7. That's just to say that electrons and photons, when they hit the detector, behave similarly. The shower developments of electrons and photons are very hard to distinguish. They look almost the same. So we talk about electron, positrons, and photons. The shower development is controlled by the radiation length. At each radiation length, the energy of the particle drops by a factor 1 over Euler constant. That's our definition of x0. The energy loss is high compared to hadronic calorimeters, and therefore electromagnetic calorimeters need not be very thick. That's the main reason why they can be made homogeneous. Electromagnetic calorimeters therefore exist both as homogeneous or as sampling calorimeters. At high energies, the Bremsstrahlung goes with z squared, the atomic number, and therefore x0, the radiation length, falls with c squared. At low energies, so that's Bremsstrahlung. At low energies, ionization losses are dominant, and the compound effect for photons. The critical energy, we defined that as the energy where the two processes are equal. So Bremsstrahlung and ionization loss on average have the same value if the particle has the critical energy. Why do I repeat this? Because it should help understand the following very simple shower model. Let's say we have a detection material and the sketch to the right, and we slice it in units of the interaction length. So each unit here has amounts to 1 interaction length of a given material. Doesn't matter which material. So our shower model is extremely simple. Let's say we start with an electron at a certain energy. It goes through the first shower length through the first radiation length, and then it interacts once, loses energy, and then a cascade develops. So that's our very simple model of shower development. And when does it stop? It stops at the critical energy. That's because below the critical energy, the 1 over beta squared term of beta Bloch takes over, and below the critical energy, thus the secondary particles thermalize. I'll explain that again on one of the following slides, but now please just take my word for it. So below the critical energy, the shower particles thermalize, and the shower development stops. And therefore, the number of radiation lengths that are needed for the calorimeter are given by the logarithm of the energy that you want to have divided by the critical energy. So let's say your critical energy is 100 MeV and you want to stop a particle of 100 GeV. You need to have a factor of 1000 in reduction. So a factor of 1000 in reduction, if we assume that the particle energy is split half-half, is just the logarithm with the base 2 of the energy ratio, and that gives us the number of interaction lengths that we need. Let's look at it in more practical terms. The plot to the right shows the depth in copper. The example is copper here, and that is an incident electron. So we shoot a 1 GeV electron on a block of copper, and the shower maximum is where my mouse cursor is here. The green shape describes the shower. Now at 10 GeV, at 100 GeV, and 1 TeV, the shower penetrates deeper inside the absorber material. But you can see that the shape maxima are roughly equidistant, which means that they are proportional to the logarithm of the energy. Not only does, so that's the left plot shows a two-dimensional view. We see that the shower maximum develops somewhere inside the few radiation lengths inside the absorber material, but not only that, the shower shape also increases a little bit. So the shower gets wider the deeper we go into the detection material. Let me give you some more background. First, to explain better why the critical energy is important. Look at the left plot. That compares the left 6 plots. That compares photons and electrons. Photons are in the first column, electrons are in the second column. Different materials are compared here. There is carbon, iron, and uranium. So from top to bottom, the atomic number increases, Z increases. That means both pair production processes, and let's discuss it for electrons maybe. The radiation losses increase with C squared. You can see that here the yellow shape increases and increases. In green are shown ionization losses, and by definition, the critical energy is where the ionization and the radiation agree. So let's look at the high Z material. I'm now at the bottom right plot. If a highly energetic particle hits, let's say a GeV, that would be at the right y-axis here, then the incident electron begins to shower. It begins to lose energy, and because it loses energy, the relevant interaction is controlled by what's to the left of the yellow shape, until the shower development continues until the critical energy is met, at which point the ionization loss takes over, the 1 over beta squared, and the shower particles very quickly thermalize. So we roll down we slowly roll down during shower development until we meet the critical energy, and then all the particles are stopped immediately. Now, if you look at the behavior of the energy loss and the radiation loss as a function of the atomic number, Let's look at it from top to bottom. You see that the critical energy is high for the low C material, and then because of the z-square dependence of the radiation loss, for the higher C materials, the critical energy reduces. That means that high C material have a higher multiplicity of lower energetic particles. If you shoot a TeV electron at the high C material, you just produce more particles with lower energy if you take a high C material instead of a low C material. Okay, some practical numbers now. For the situation for the photon is similar. Some practical numbers. We want to contain the full shower in our calorimeter. How deep does it have to be? How many radiation lengths do we need? About 95% of the energy of an incident particle is contained within a depth that is the logarithm that we computed on the previous page, and then an offset of 10 essentially, and then a little correction as a function of C. That's an empirical formula. The rule of thumb is just take a 25 interaction length. So if the interaction length is small, the electromagnetic calorimeter can be compact. So rule of thumb, 25, and you're good up to the TeV scale. Now let's look at the transverse plane. Just so you understand. Let me make a small sketch. Let me make a small sketch here. I hope this is helpful. We talk about, oops, can I remove this again? We talk about the shower development. So particle starts here and then creates a shower. We want to know how deep the calorimeter has to be. That would be our T. I'm sorry, no, this is probably not very helpful. Let me try to make our shower look a little bit nicer. That's the detection material here. But we also want to know how large the transverse size of the shower is. Now, in the transverse plane, 90 or 95% of the shower are contained within 1 Moliere radii. That's exactly equivalent to what we have discussed in lecture 3 when we discussed multiple particle scattering. The rule of thumb is divide 21 MeV by the critical energy and multiply with the radiation length. And that's the radius of the shower that contains 90% of the particles. If you want to have 95% of your particles, then just multiply by 2. Take 2 Moliere radii. The transverse shower profile of such a shower is a very dense central core with a high density of particles in which almost all the energy is deposited. So 90% within 1 Moliere radii, and only 5% more in the second one. It's therefore a dense core surrounded by a halo of just a few particles. The width of the core is determined simply by the small angle scattering of the electrons, and the halo develops because of photons. They can travel a larger distance in the detector, and also by large angle Rutherford scattering, which we have discussed in the second lecture. So that's the processes that lead to the transverse spread in the shower development. If we look here, if we look to the right here, 9 MeV, for example, for a high Z absorber means that the Molière radius grows. That means a high Z material will produce more particles than a low Z absorber. It will produce them at a lower energy, and the shower will be wider. The showers in low Z absorbers are narrower. Okay, let's look at the energy resolution, because after all, shower development is fine for constructing the detector. We have to understand it, but once the detector is constructed, it's all about the energy resolution. That is the quantity that we want to measure. In an ideal homogeneous calorimeter with infinite dimensions that records everything with 0 thresholds, the resolution is determined simply by the statistical fluctuations of the number of shower particles. So the resolution, the relative energy resolution, is proportional to the fluctuation in the number of particles that are recorded divided by the number of particles, because the energy is proportional to the number of particles. Now, the fluctuation of a stochastic process is this stochastic process is proportional to the square root of n. The square root of n divided by n is just 1 over the square root of n, and this therefore is proportional to 1 over the square root of energy. So simply by means of the stochastic fluctuations of the number of shower particles, we get a resolution component that falls with energy. Let me clear this again. In sampling calorimeters, this number has to be reduced to the number of particles that are produced in the detection material, and the number of particles that are produced in the absorber, of course, are not recorded. Moreover, there's of course a threshold energy. Below the threshold energy, a particle is no longer recorded. We've discussed many detection principles in the previous slide, so let's compare a few. For silicon sensors, the threshold energy is low. It is the energy that's required to produce an electron hole pair, and it is in the electron volt range. For gas detectors, we talk about 10 times more, 30 eV or so for an electron ion pair. In plastic scintillators, we talk about 100 electron volts. Neither of these numbers is good or bad. It depends on the detection, the detector application, the readout electronics, the efficiency in collecting the signals, and many more quantities. Similarly, I've already explained it here, write it down. In sampling calorimeters, the number that enters, the number that's relevant is the number of visible particles above the threshold and reduced to the number of particles produced in the detection volume. But other than that, the formula is the same. It's 1 over square root of visible particles, which is proportional to 1 over the square root of energy. And therefore, calorimetric measurements become easier at high energy because you have more particles. Spectrometer measurement, like a tracker, becomes more difficult at high energy because the path is less bent, the curvature radius is larger. So that's why calorimeter and spectrometers are complementary as a function of energy. Another limiting factor, well, problematic features in calorimeters are the Lambda fluctuations. In sampling calorimeters with small detector layers, because you want to build, for example, a calorimeter, you want to build it very compact, you use a lot of absorber and there's little space left for the detector, then the thin detector is subject to Lambda fluctuations, as we've discussed in lecture 3. These are non-Gaussian, this is a non-Gaussian stochastic process that originates from large angle deflections from Coulomb scattering of electromagnetically interacting particles. So if you forgot what Lambda fluctuations are, was discussed in lecture 3. So for thin detectors, that's a particularly important problem. And then track length fluctuations for collider experiments are important as well. The secondary particles are scattered around in the detector. They may therefore cross the detector plane in different angles, and therefore the ionization signal, for example, or the deposited signal is fluctuates with changes with the angle at which the secondary particle has been deflected. These track length fluctuation also limit the energy resolution. So we have discussed a few terms that enter the energy resolution. Let's put it together. The energy resolution of a calorimeter can be parameterized by this simple square root formula. The first term is the stochastic intrinsic resolution. Just remove the other two terms, let the square root kill the square, and you realize that the first term here is the intrinsic stochastic energy resolution proportional to the square root of energy. The second term that falls with 1 over E is mainly due to the electronic noise. This is a constant term. Why is it constant? If you take the second term and let the square root remove the square, then the energy here cancels, and the contribution is therefore independent of energy. It is used to describe noise, for example, electronic noise that's always present independent of the energy. Pileup fluctuations, that's particles that come from a different collision, would also be independent of the energy of the particle under consideration. So there's a certain number of contributions that just add a few GeV with, for example, a few GeV to a particle independent of the energy of that particle, and that would be described by the third term. The third one is critical because it limits the high energy resolution. It grows with energy. If you let the square root remove the square, you multiply with E, you find that the resolution grows, the resolution term grows with energy, or in other words, the relative, it's constant, it's a constant term in the relative resolution. So for asymptotically large energies, the relative energy resolution cannot get better than the third constant here. It is, we will make a small calculation, but it is caused by the inhomogeneous detector response. Before we do this calculation, let's look at the different contribution as a function to the energy. So in this example, this is only a schematic plot. We have sampling fluctuations, we have track length fluctuations, we have Lambda fluctuations, and adding these cause this square root behavior and the plateauing at the value of C3. So in this example, already at the future EV, the resolution levels out and is constant. At high energies, the constant term always dominates. At low energy, the stochastic term always dominates. That's the main message here. Let's do this in a second. Let's compare the calorimeters in a second. I want to now motivate with a simple calculation what I've discussed. I'm sharing the screen. Oops. Let's say we have an incident particle on our calorimeter, and a shower develops. Let's say this is a hadronic calorimeter, and we record now. We reconstruct an energy that is a function of the true energy. And let's say our shower has an electromagnetic and an hadronic component. So we take the hadronic fraction of the shower energy, and it receives the hadronic response. So we have a hadronic calorimeter. For example, that could be our HCal. We have a hadronic fraction of the energy. And then we have an electromagnetic calorimeter. And we have an electromagnetic fraction that I write as 1 minus the hadronic fraction. And that's also multiplied by the true energy that we had before. So let's compute now the uncertainty in the reconstructed energy. By Gauss law, this is simply the derivative of the reconstructed energy with respect to the hadronic fraction times the fluctuation of the hadronic fraction. So our model is the following. We have a certain true energy that we want to know. We have a fraction of the hadronic and electromagnetic energy that fluctuates. Sometimes, let's say, this is with 40% hadronic fraction, and sometimes with 60% hadronic fraction. And in the next event, we have 60% here, and we have 40% electromagnetic fraction. And in the next event, this number changes. So the situation is that we have a stochastic fluctuation of the energy with respect to whether it is deposited in the hadronic calorimetry or in the electromagnetic calorimeter. And now we compute how bad it is that the responses of two calorimeter systems are different. And we are already done, because we only need to differentiate. And if we differentiate with respect to the hadronic fraction, the result is immediately RH minus R electromagnetic squared times E true squared times times the fluctuation of the hadronic component. Now, if we take the square root of this formula, we immediately find that the resolution in the reconstructed energy is the absolute difference of the responses of the hadronic and the electromagnetic calorimeter, multiplied with the fluctuation of the energy and multiplied with the true energy. In other words, sigma over E is some constant times the response difference. Okay? In other words, if there are energy components in our calorimetry that are recorded with different responses, we will find this will determine our asymptotic resolution. If we go back, let me unshare this simple calculation. I will put this in more context. We'll put this in more context in a moment, but let me repeat. If we have, for example, a pion hitting an electromagnetic and hadronic calorimeter, and the responses are different, then we will find a large number, or then we will find a correspondingly larger number of the asymptotic energy resolution. In other words, if you have two calorimeters and you don't know which one did what fraction of the total energy, then that limits how well your energy measurement can perform. If you have a calorimeter that has the same response for all particle species that you do not distinguish, then your asymptotic resolution can become arbitrarily good. All right, we will discuss this. We will discuss this in a little bit once more. Let's now compare electromagnetic calorimeters. Typical values. What's a good calorimeter? Lead tungstate of CMS has a depth of 25 radiation length. That's plenty. Is an excellent 3% over square root E. 3% over square root E. That's a test beam result. Calorimeter with a very small constant term of 0.5%, despite the fact that it is nonlinear. Sodium iodide, these are different. The sodium iodide calorimeters shown here are ballpark similar. These are smaller calorimeters. The sampling calorimeters are shown to the right, so the left ones are homogeneous, the right ones are sampling. The example that we've discussed also with 25 interaction length is the liquid argon Atlas accordion calorimeter with liquid argon and lead as the absorber. It has a somewhat worse energy resolution. However, by now the radiation damage in the CMS calorimeter is compensating. In other words, the fact that Atlas can purify the liquid argon makes the calorimeter performance now, I think, roughly equal. It depends on where we are in the detector. For the forward region, more closer to the beam, the degradation of the Atlas crystal calorimeter is already sizable. Okay, so these are comparisons of different electromagnetic calorimeters. Now, the second type of hadronic calorimeters are hadron calorimeters. Those measure the energy of charged and neutral hadrons. What are charged and neutral hadrons? Pions, neutrons, protons, lambdas, and everything else that is long-lived enough such that the particle can travel from the interaction point to the detector. The shower development is actually similar to the electromagnetic calorimeters. It's a stochastic process, but the strong interaction governs it. And in the first few interactions, it is determined how much energy is going into the electromagnetic component. We'll repeat this discussion. The shower development scales with the nuclear absorption length lambda, and that is a larger number, and hence Hadron Calorimeters, when compared to electromagnetic calorimeters for particles of the same electron, here we compare electrons and pions, they need to be thicker. The example here is an ion absorber. We shoot a 100 GeV pion into an ion block. It can traverse the whole, the whole 1.5 meters of ion, while an electron cannot do that. It will shower electromagnetically much earlier. The importance of calorimeter measurements of hadrons has to be underlined, because for the neutral hadrons, it's really the only way to measure the energy of those particles. A neutron, for example, is not charged. It will not give an ionization signal. It is invisible in the tracker and in other ionization detectors, and hence it needs to be showered. So it must be stopped with a material with large nuclei, and then that hadronic shower must be measured. Therefore, these hadron calorimeters are extremely important, because a large fraction of the energy, a large class of particles that are produced in hadron colliders, also at lepton colliders for many processes, are neutral hadrons. Hadron calorimeters, as we've discussed, only exist as sampling calorimeters for this reason. I mean, a 100 GeV pion, you need a 150 centimeter of steel to stop it. There's no way we can replace the steel here with a material with a nucleus with a smaller mass number. The required length, the required depth would be prohibitive. Because of this, because the different shower comparisons in an experimental setup, the electromagnetic calorimeter is always in front of the hadronic calorimeter, just because the electromagnetic shower could not reach the calorimetry if it was otherwise. Because the electromagnetic calorimeter is in front of the hadronic calorimeter, once you have a hadronic particle going through, the electromagnetic calorimeter always also acts as a hadronic calorimeter. A neutron going through the electromagnetic calorimeter does not know that it's supposed to wait for the hadronic calorimeter. If it sees a nucleus, it will start to shower. In CMS, the electromagnetic calorimeter that stops all the electrons and the photons is about 1 lambda, 1 nuclear interaction length in front of the HCal. So on average, one interaction happens in the equal even for a neutron. But the lead tungsten is not dense enough, and hence the real shower, the bulk of the shower development happens in the hadronic calorimeter. To repeat what we've said on hadronic showers, hadrons interact inelastically with single nuclei in the nucleus. So imagine a highly energetic neutron hitting a nucleus, setting off a cascade of hadrons, protons, neutrons, pions that hit further nuclei. We know that in particular, the neutral hadrons can travel a long distance in the material until they set off further reactions, and hence the showers extend much deeper in when comparing electromagnetic and the strong interaction. if neutral pions are produced, the pi zeros always decay to photons. Photons are an electromagnetic component. So in the beginning of the shower development, as it is decided probabilistically, of course, what energy fraction goes into the electromagnetic component. It can happen that the incident neutron is the majority of its energy is converted into neutral pions, and then you get something that looks like an electromagnetic shower. That need not be the case. Maybe neutrons and protons are produced, then the then the resulting energy is more on the side of the hadronic energy fraction. Between the hadronic interactions, so let's say a proton is traveling from one nucleus to the next, the charged particles, for example, the protons, the pions, or the charged kaons here, they also ionize the material, leading to further electromagnetic signal. That is to say that depending on stochastic and uncontrollable processes in the shower development, there's always an electromagnetic component coming with the hadronic interaction, and it fluctuates widely. This limits the resolution in reconstructing the energy of the incident, the energy of the incident particle. Maybe I should write it. Maybe I should write it down again, because we already did. The calculation. One second. We already did the calculation. The relative energy resolution in this case is a constant times the absolute value of the response difference of the electromagnetic and the hadronic calorimeter. So if your response on the electromagnetic, let me erase this. If the response on the electromagnetic component is 90% and on the hadronic component it's 80%, you have a 10% difference in your responses to the two components. If your fluctuation is, if the fluctuation has an average of 40%, then you get a 4% uncertainty just from the fluctuation of the shower. Okay, that's what limits the energy resolution at high energies. Let's now look at the shower dimensions. Hadronic shower dimensions are similarly described as for the electromagnetic calorimetry by a length parameter. It's called the nuclear absorption length. 95% of the shower is contained in roughly 7.6 is here 7.6 absorption length. That amounts to 80 centimeter in uranium. Uranium is expensive, not easily available, but that's as short as it gets. Rule of thumb is to take 10 absorption length. 95% of the total energy is deposited in a small cylinder with a radius of that radiation length, typically a few, so in case of uranium, a few centimeters. The transverse energy profile, therefore, similarly to the electromagnetic case, is a highly energetic core with a halo of low energetic particles. There are other processes that limit the resolution of hadronic shower reconstruction, or the measurement of incident hadronic particles, and that's the fact that there are hadronic showers involve processes that lead to energy loss because they create non-measurable signals. One is nuclear binding energy. So if there's a nuclear reaction, that the binding energy is simply absorbed and not reconstructed. Neutrinos can be produced. Also, highly energetic muons can be produced and leave the detector without, if there's no muon detector outside, this cannot be corrected. So neutrinos for sure leave the detector without interactions. Highly energetic muons may be recorded if there is a muon system, otherwise they are lost. And then there is also kinetic energy lost in the debris that's flying around from the nuclear interactions. We have already discussed that the hadronic showers always also produce an electromagnetic component, and the fraction of the shower energy which goes into the electromagnetic shower is determined in the first few or so interactions, when it is essentially, when either pi zeros are produced or they are not produced. That means we have large event-by-event fluctuations for the hadronic shower development. And I've calculated that if the electromagnetic and the hadronic response are not identical, it leads to a worsening of the resolution and no improvement, and no more improvement with the square root of the energy that is otherwise there. So it is the asymptotic limit of how good we can make our calorimeter. To the right, there's a comparison of the absorption length for different materials. So uranium is the shortest, that's still practical. Lead is a good choice. Iron and lead are similar. Copper, we've had an example of. Silicon is a lot worse. But silicon is used in is not an absorber material. Okay, one thing that is just for fun is a special feature of some calorimeters. Those are compensating calorimeters. Remember, if the response of the calorimeter to the electromagnetic and the hadronic component of the shower differ, then, as we've calculated, the reconstructed energy uncertainty is proportional to the energy and to the response difference and to the amount by which the hadronic component fluctuates. Now, now what we can do is to make the response difference zero. In other words, to have a calorimeter which has the same response to the electromagnetic component of the shower, that's electrons and photons, and the hadronic component of the shower. That can be achieved by a careful choice of the calorimeter active material and the absorber. Typically, one needs to tune the absorber material in terms of C. One takes a large C absorber and a detector with low C. Then if the detector geometry is optimized in terms of thickness of both the detector and the absorber, and if the signal processing disregards the slower hadronic component that can be initiated, for example, for gamma emission of excited nuclei that happen at a larger timescale of, let's say, above 100 nanoseconds. So if this component that's hard to control is removed by a fast readout, then in principle, a little bit in practice, a ratio of the shower response of 1 can be achieved for the electromagnetic and the hadronic response. Remember, this delta R here that limits the resolution is the difference of these two. A calorimeter that is called, a calorimeter with this feature is called compensating, because whatever the shower does, it doesn't matter whether it's more on the hadronic side or more on the electromagnetic side, the reconstructed energy of the component is the same if the response is the same. The compensating calorimeters therefore are therefore linear over a large energy range and have a better resolution. Here, the plot to the right shows what can be achieved. There are several scintillating calorimeters compared. The CDHS are the green dots. It has a ratio of the response of electromagnetic to hadronic of 1.3. And you can see that the energy loss grows with energy, so that grows linearly with energy, so that the relative energy loss is constant, while the compensating calorimeter from the Helios experiment, which was carefully designed to achieve a compensating response very close to 1. It's the black dots below here is completely constant over a large energy range. That's an example of how compensating calorimeters and a careful choice of all the components lead to a supreme energy resolution. Okay, comparison of Hadron Calorimeters, recent ones and not so recent ones. The Zeus scintillator calorimeter at DESY was almost compensating. Absorber material was lead. The two largest calorimeters, well, the two calorimeters in the largest general purpose experiments are the Atlas and the CMS hadronic calorimeter. Atlas uses in the end cap liquid ion sampling calorimeter with brass. CMS uses as a hadron calorimeter a scintillator. We're going to see that in the next slides. A scintillator with a brass absorber. All these calorimeters are non-linear and therefore have a constant term in the energy resolution that can be sizable. Atlas in the barrel uses a scintillator as well. So typical energy resolution, and that's really what defines the experiments. You see that Atlas is doing much better than CMS. The CMS scintillator, HCal interleaved with brass, has an energy resolution of 100% over square root energy. So let's say a 100 GeV pion going into the hadronic calorimeter has a 10% energy resolution, and that's really not great. Anyway, that is the compromise that was taken. So let's look at a few concrete examples. I also need to keep what's the time? Let me check the time. Oh, we have a few more minutes left. Let us look at a few examples. First is the lead tungsten electromagnetic calorimeter of CMS. This is a 3D view. It's split in what we call supermodules of 1,700 crystals. These are lead tungsten scintillating inorganic crystal calorimeter. There are a total of 61,000 crystals in extremely fine granularity of 2 times 2 centimeters. The end caps have 3 times 3 crystals, somewhat coarser granularity, and roughly 15,000 crystals. So this is what the assembly looks like. Inside the equal are the silicon tracking detectors. Outside is the Hadron Calirometer. Few pictures from the fabrication. Top left is the ingot from the Cholchalsky process. That's the lead tungsten crystal that's cut into these rectangular shapes. I'm very sorry that I cannot show you or hand you over such a crystal. It's really impressive how heavy it is. While it is still transparent. And the other two images here show the readout. The end cap uses vacuum phototriodes. The barrel uses APDs, avalanche phototriodes, which are matched to the wavelength of the scintillating light. The test beam measurement, we have had it before, is extremely good, 3% over square root energy for the electromagnetic calorimeter. So CMS really has absolutely great electromagnetic calorimeter. The Hadron Calirometer was a compromise, an interesting one. The absorber is brass, thickness of 5 centimeters, interleaved with plastic scintillator. Plastic scintillator is shown here with wavelength shifting fibers. So the scintillation light is 400 nanometers. The fibers absorb and re-emit at 490 nanometers, which is matched to the hybrid photodiodes. Hybrid photodiodes have in 2017 been replaced with silicon photomultipliers. The energy resolution of that configuration is not so great, 100% over square root energy. You can see here in this image of the HCal barrel, you can see here the sampling structure in this detector, in this photon. That's the transverse sampling structure of the Hadron Calirometer. Atlas has a liquid argon electromagnetic calorimeter. It's what we call an accordion calorimeter, and it covers most of the instrumented area, so almost 4 pi. This is a sampling electromagnetic calorimeter with a lead absorber. So what you see here is you see here the lead absorber with spacers. So there is this accordion structure, and between several of such layers of lead absorbers are electrodes. We'll discuss in a moment what these electrodes do. The geometric configuration is shown at the bottom. So that's how this accordion is placed in the detector, particle coming from the right and showering. The granularity of the detector, let's look at it here. The granularity of the detector is closest at the beginning of the shower. So where my mouse cursor is, this is where the particle trajectory travels, for example, an electron or a photon. And then there is a very fine granularity of the readout in the beginning, because the shower, that is when the shower profile is best measured, and the granularity then reduces in steps as the particle shower develops deeper in the detector material. No. The configuration of this calorimeter is as follows. There is liquid argon here. The charged particles from the shower create an ionization signal. This ionization signal must be picked up by an electrode, and hence one needs a high voltage supply here to have the charge carriers move. So there are two liquid argon gaps. These are the detector, the liquid argon detectors based on recording the ionization, producing and recording the ionization signal, and in between the liquid, the lead absorbing material. The last example is, because it's funny, the H1 Spaghetti Calorimeter. In this type of calorimeter, there are parallel bundles of scintillating fibers that are absorbed in a matrix. The fiber diameter is 0.5 to 1 millimeter. This is a very fine structure for a calorimeter, and it is still cheap. It can also be compensating because the geometric properties can fully be controlled. The spacing of the fibers and the geometry of the fibers here in this hexagonal shape can be controlled such that the calorimeter is compensating, which means it has the same energy response to the electromagnetic and the hadronic shower component. It's also completely hermetic. The full detector is covered. There are no cracks here. The main disadvantage is that it does not allow longitudinal segmentation. For a hadronic calorimeter, one wants longitudinal segmentation to get some information on the depth of the shower, but one cannot cut the fiber because then it is cut. So there's no longitudinal segmentation here. There's shown a prototype here with 1 millimeter thick fibers, and this is an hadronic calorimeter with 30% of a square root of energy resolution, which is really quite excellent. Okay, that was the last example. We are at the end of our discussion of calorimeters. I stop the recording.